Good morning, greetings, everyone who is present here and you who is there watching the live stream. I hope you have enjoyed the content for the past day and the ones who have been attending the workshops for the past 2 days. As I've been saying, 1, 2, 3, and we start 1st, 2nd, and 3rd of October is the CyberChess conference to start our European Cybersecurity Month. CERT.LV, together with the partners, is bringing you the world-class speakers and the themes that are emerging and ever important in the changing world. Now, I would like to introduce my next speaker, Max. And, well, if you were here on the first day, he was giving also the workshop on Golang reverse engineering. That's going to be also related to his talk. And also, I would like, as he comes onto the stage, with an applause, he also got the first place in the chess tournament that happened on the 1st of October. With this, Max, welcome on the stage.
Okay, thank you for the kind words, and thank you for having me. So yes, as you just said, welcome to my talk about an introduction about reverse engineering Go malware. So about me, my name is Max Ufer. I'm a security researcher and malware analyst at the Fraunhofer FKE. I'm also a lecturer at the University of Bonn on binary analysis in general. And yes, I'm interested in anything low-level reverse engineering, binary analysis. So what are we going to talk about today? First, we're going to talk a little bit about Go in general, then about Go in the current malware landscape, and then we will dive into the contents of Go binaries. So we will talk about the components of a Go binary, about the distinct language features, which are maybe different from other languages, and how we can analyze them easier. And then I will tell you about some useful tools and practical tips. So, I have to warn you now, this presentation starts with a jump scare. This is a nice little harmless Hello World program in Go with a sweet little gopher on the top. And this is what it looks like when you open it in your favorite disassembler. So you have many things which you maybe didn't expect. So you have some conditional jumps in the beginning. You have these scary-looking XMM registers. You have some abstract objects which are being referenced. Nothing that you would expect from a simple Hello World binary. But the goal of this talk is to take the fear away from you when you see something like this and show you that analyzing Go doesn't have to be that hard as it appears in the beginning. So about the Go programming language, a small introduction. It was created by Google in 2007 initially and was publicly released in 2012. The development was fueled by frustration over C++, which I think many people can relate to in the audience. Everyone who's I've talked to who developed something in C++ at least can relate in some way. Here's a direct quote. They wanted to improve programming productivity in an era of multi-core network machines and large code bases, and wanted to create a fast, statically typed, compiled language that feels like a dynamically typed, interpreted language. So basically, they tried to achieve a language which is as efficient as C, as usable as Python, but also memory safe, and offers this thing which is always referred to as effortless concurrency. So all these advantages have also attracted many malware authors. As you can see already in 2020 or 2021, there were many articles which were claiming this now is the year of Go malware. Now everyone's going to use Go. Obviously not everyone, but in my experience, it's getting more and more. A quick search on Malpedia already showed 50+ families which reference the Go language in the description of the malware. this is just the lower bound, as many families in Wikipedia don't even have a description, so the real number is much higher. And yeah, the main advantage for malware authors in Go, I think, is it's quite easy to write, but it's quote-unquote hard to analyze and hard to detect, at least right now. Another advantage is that it's cross-platform, so if you're, for example, developing your favorite DDoS botnet and you want to support multiple platforms, it's very easy in Go. You can just cross-compile it for every platform that you want to target, and you're good to go. Yeah, and it has been used in many different domains, for example, in ransomware, the Hello Kitty ransomware, or the Night ransomware, which is now extinct because it, because now Ransom Hub has taken its place, which at least partly has been created on the same source code base of Night, and now is one of the biggest ransomware threats currently active. It's been used in the DDoS domain, as I've said before. On the one hand, for example, the DDoSia project, which is like this volunteer network of people based or supporting the Russian Federation to carry out DDoS attacks against NATO allied states. CyberShock was another example that I've just analyzed recently, and it's also been used in other domains like rats, like the Blue Shell rat or the Zabroki rat, just to name a few recent examples. So, but let's dive right into the binaries. So I've just showed you the how the assembly of this small Hello World program looks like, and you've seen that it was relatively large for this simple Hello World functionality. And this also reflects in the size of the binary, but in an even bigger way than you might expect. So a simple Hello World binary, when created in C, is about 16 kilobytes big, at least on my machine. You can get it way lower if you try. But this simple Hello World program is already 1.7 megabytes large. And if you look at the symbols in this program, it contains more than 2,000 symbols already. And the reason for this is that Go binaries are completely self-contained. They have all these high-level features like garbage collection, concurrency, and these easy-to-use language features, which try to make development more easier, but these are all contained in the binary, all the runtime stuff, not like other languages, which are, for example, based on .NET. So all this stuff has to go somewhere. And this is one of the first issues that you will encounter when you try to analyze a Go binary. Because if you analyze a Go binary, for example, you just open it up in Gira and don't do anything, it will look like this. It's a little bit small here, but I think you can see there is like a whole load of functions on the left side. Also, the decompiled output is quite confusing. And yeah, this is still just the Hello World binary, but it contains more than 2,000 functions. And yeah, when you open this at the first time, maybe you don't even know where to start. So how can we tackle this? The main thing that we can use if we have just regular Go binaries is we can abuse one feature of Go, which I will present now. Consider this simple C program. You have an array, it has 10 elements, and then you try to access an element which is far off. What will happen? Segmentation fault. Now you have a similar thing, but in Go, like an array, and you try to access it out of bounds. Of course, you also get an error, but this error is much more verbose. It shows you the exact location in the source code where the error happened, and which function it was in, but also which source code file it was, what kind of error it was. So this means this information about the program has to be stored somewhere in the binary, so these stack traces can be created. And this is exactly what the program counter line table is for. So this is a graphic that I've taken from a very nice blog post from Google from 2022. And the program counter line table is a component which every Go binary in some sort has. The nice thing is also stripped binaries have this program counter line table because it's referred to by the runtime. In ALFA files, it's a dedicated section which is called Go PCLN-tab. In macro files, it's also a section. In PE files, it's a little bit more difficult. It's referenced to by the symbol table, but even if the symbol table is not present, we can still find it because it starts with a magic, which is always, so some magic bytes. They are version dependent, but they are always there in this table. So what the tools that I will show you now later on will do, they will just scan the binary for this magic bytes, and then they will locate this procedure. No, I always have to say procedure line table, program counter line table. And what this table contains is, on the one hand, it contains the function boundaries of all functions. So it is used by the Go runtime to map virtual addresses back to these functions to create these nice stack traces. And it also contains all type information, which usually would be lost during compilation. So as I said, this table is always present in Go binaries. It can be corrupted if the binary is obfuscated, but we will talk about how to deal with this later a little bit. But in a regular Go binary, you will always have this table. We can abuse this to recover all function names in a Go binary, even if it's stripped, which is very nice just because we have so many functions which we don't want to look at because they are just part of the runtime. There's also another structure which is displayed here, the module data structure. This also contains some nice meta information, like information about the Git repository the source code was in, and about the version and compile options. So this is also a nice little benefit. So this is just a short overview. If you want to know this in more detail, I would refer you to this blog post by Google. It goes into some more depth. So this is what a decompiler output looks like when you actually parse this structure. And the nice thing is, at least IDA does this by themselves. So this is not a sales pitch for IDA, but in my experience, IDA handles Go binaries, at least since version 8.2, quite well out of the gate. In other decompilers like in Ghidra, you have to deal with some plugins to do this, but IDA actually scans through the binary for this program counter line table also when the symbol table has been stripped, and it creates this very nice output, which renames all the functions to the original names. It lists them on the left side in a folded structure, so you can have this package hierarchy restored. And it also restores all the type information. And you can already see on the right side in the decompiled output that it looks way nicer. It almost looks like source code again. Yeah, and right now I've only told you about all the bad things that we have to deal with because of these many runtime functions which are part of a Go binary. But when we have recovered these names, it can actually make our jobs a lot easier. As Go is a high-level language, or a higher-level language, it deals with higher-level structures, and these structures are handled by runtime functions. So if we know which functions are the runtime functions and with which kind of objects they interact with, we can actually make use of this to quickly or more quickly understand what a function does without getting lost in all the details. So one example. You have this function here on the right. As you can see, it has already more than 500 lines, and we are not even at the end. There's much stuff going on. And if you would analyze this in detail just from this output, you would probably take some really long time. But if we just focus on the runtime calls which are being made here, which are nicely restored by IDA in this case, we can see this on the left. This is the function calls window, which just lists all function calls which are performed in this function. We can see that this function first makes many calls to some operations regarding slices, so like the Go equivalent of arrays, to put it simply. It converts some byte slices to strings, and then it calls the net HTTP new request with context function. So only from this, without looking at the code, you can already infer some functionality about the binary. So what probably can happen, and actually happens here, is you have some byte string which is being transformed in some way, converted to a string, and then an HTTP request is being created. So what you can now create as an hypothesis is maybe here is some string being decrypted, which is maybe related to some C2 functionality, and then an HTTP request is being created. And this is actually what's happening in this function. So if you now want to extract, for example, the C2 domains, of course you have to now go into more detail, but just by looking at these runtime functions, you now already have this overview which guides you in where to look to find this information that you're interested in this large binary, which takes multiple megabytes. So, when analyzing binaries, we usually have two ways how we can start. One way is to start at the entry point, to just get a broad overview what the binary does in general. So how do we actually find the main function in a Go binary? Well, if we just have this regular binary, it's very easy. Just look for the main function, because the function names are restored, and you can just search for it, and then you open it, and then you're good. But what if you see something like this? This is an example of a program which was obfuscated with the open source obfuscator Garble. And one of the many things that it does is it corrupts the program line counter table. So we're not able anymore to recover the function names. So now you're again left in this situation where you have this big binary with many functions and you don't know where to start. There are two ways how we can deal with this situation. The one way is the Go compiler is a bit predictive in its behavior. One thing that it always does is it always puts the runtime functions at the start and the user functions at the end. So one easy way that you can do just to get to the user part is you just look at the functions which are at the bottom, and then you go through the cross references backwards. But this can, depending on the size of a binary, of course, take a very long time. So if you want to follow a more structured approach, we can look at this function here. This function is the runtime main function. It's the internal function of a Go binary which launches the main function. And it looks maybe a bit overwhelming at the start, but this is the end of the function. And this is the call to the main function. So at least in the current version of Go, and in most of the samples, or all of the samples that I looked at, you will have this kind of structure in this function. So you have, especially what I always look for is this comparison at the bottom, the if with the two memory locations which are being checked, and then a call to a function which is not recognized by either. And this should be the main function then. This runtime main function is usually recognized by IDA as a library function due to their signatures, which is very nice. But you can also find it quite easily otherwise, if maybe something changes in the future and these signatures don't match anymore and you still need to find it. What you can do is you just look at the entry point of the binary, or the first function that is actually being executed, and then you go to the end of this function. And there you will see something like this. So you will see a few function calls, and before the third to last function call, an offset is being loaded. And it is actually passed to this, what is here called runtime bad mem call. And this offset here, this actually contains, after one more layer of indirection, the address of the runtime main function, so the thing you can see here on the right. And if you have found this, you can use this to find the runtime main function, and if you have this, you can use this to find the main function. So the other way, which we usually do things, is we don't start at the main function, but we look for this, what we always call cornerstones. So you look for these interesting things in the binary, like imports or, for example, strings, and then you go backwards from them and see in which context are they used. So let's start with strings. Strings are handled a bit differently in Go. So let's go back to our Hello World program. And if we run a tool like the Linux strings tool on it, we will see something like this. So we will see very large strings with seemingly no end. And yeah, this is a bit annoying because now we cannot directly see which strings are actually used in binaries and where they start and where they stop. And the reason for this is that they are represented differently than in, for example, C binaries. So this is how a basic C string looks like in a binary. So you have just ASCII characters, and then they are terminated by a 0 byte. This is how the same thing looks in Go. As most of you probably realize, this is not a string. It contains many 0 bytes, but it's actually a struct. And it starts with a pointer in the beginning, and then something which looks like a number. And this is actually how strings look like in Go. So you have like this struct definition where you have first a pointer to the data, and then a different variable which tells you the length of the string. And looking at the data, you will then there see the string, but without the 0 byte. So amazingly, we save 1 byte at the cost of 8 bytes, which tell us the length. It's really amazing. Yeah, so this is how strings are handled internally. Another thing which is important to understand when looking at these binaries is the calling convention. As you probably all know, calling conventions differ from different platforms and different programming languages, and Go is no exception for that, because Go created its own calling convention, and it also changed over time. So it used to be, before version 1.17, entirely stack-based. Now it's entirely register-based, except when it's not. So have a look at this simple Go program. At the bottom you have the main function, and what it basically does is it reads some input and then calls a function and checks an error. And already there you see a pattern which is very common for Go. Go allows functions to have multiple return values. And what you can see there at the bottom, especially when the vals function is being called, usual pattern is you have 2 return values for a function. One is like the actual return value, and the second one is an error. And then after you call a function, you check if the error is nil. If it is not, you have to handle the error. And if it is not nil, you have to handle the error. And if it is nil, you can proceed and use the return value. Let's see how this reflects in assembly. So this is like an excerpt of this program, how it looks like in assembly. So here's this call to the function which will first convert the arguments which are passed on the command line into an integer. As I already told before, in modern Go, since 1.17, we are now at 1.23, the calling convention is entirely register-based when possible. So this means arguments are passed in registers, and return values are also passed in registers, and they're actually passed in their same registers. So the first argument is passed in RAX, the second in RBX, the third in RCX, the fourth in RDX, and so on. And if you have multiple return values, you can also have more than 2. It will be the same. So the first in RAX, the second in RBX, third in RCX, and so on. If you have too many values, for example, when you pass large structs, because struct fields, as we will see in a short time, are also passed as if they were separate arguments, then Go will switch back to a stack-based calling convention. So the motto here is either we have everything in registers or everything on the stack, but we never mix those two things. And there's an advantage to this calling convention, which we will see in a minute. So here, the stringconf a2i function, which you can see on the right, it actually gets 2 arguments here. So there's a memory reference loaded into RCX in the beginning. This is the memory location where the command line arguments are located. And then there are two values from certain offsets loaded into RAX and RBX. If you remember from the last slide, this is how Go handles strings. So in RAX, it loads the pointer to the raw string, and in RBX, it loads the length. And this struct is then passed to the a2i function. So as I just said, when we pass structs by value, internally it looks like the function gets multiple arguments, but it's actually one big struct. Then the vals function is called, but here only values are moved to EBX and ECX, and then the vals function is called. But we see we actually have 3 arguments which should be passed to vals. And this is like one small advantage of this kind of calling convention, that you have the return values and the arguments in the same registers. This just directly results in that you can chain function calls if the return value is the first argument of the same call. And this is something that you will see very regularly in Go binaries. So you can just have multiple calls, even especially if they only get 1 argument. You can just have multiple calls chained to each other, and it will look like on the first glance that they all don't get any input, but it's actually the return value of the previous function. So here we have just as I said, the array_x value is like set implicitly because it is set by the previous function, and then it is passed to the next function, to the vals function. And this thing at the bottom is just this structure which you will often see because it's this Go error handling. So you have like rbx, which is the second return value, which is being checked if it's null, and then depending on what happens, we continue in different parts of the binary. Let's have a look how this looks in the decompiler. So this is the decompiled output for the previous program. And this is the control flow graph of the assembly. So if you're attentive, you will notice two things. First of all, there's a branch at the beginning, which wasn't present in the binary. So it's, you can see my laser pointer now, but it's like this loop which is created here. This is a part of every Go function because to enable this effortless concurrency, which we'll talk about in a second, Go functions have a very small stack, so they don't take up lots of memory. So at the beginning of each Go function, the program checks, do I have actually enough stack? And if we don't, we first handle this, we increase the stack, we get more memory, and then the function loops back to its beginning and starts to execute again. So this is the first thing which you will have in every Go function, which you can basically ignore most of the time. Then the second thing is, if we go back to the code, you would actually expect the branch at the end here after the vals call. But IDA doesn't display this here. So you just have the call to main vals, and then weird memory offsets are loaded, which is never a good sign in a decompiler, because it usually tells you that IDA didn't understand something correctly, and then one print line call. Yeah, and this is just a direct result. So this part is just a direct result because of IDA not correctly parsing or correctly interpreting the calling convention in this case. So IDA understands the Go calling convention, but here it just made a mistake. And we can very simply help IDA to display the right stuff by just creating a struct which represents this, these two return values. So in the pseudocode, we will have these multiple return values simply as structs. And here we just create a struct which has, on the one hand has this integer result, and on the other hand has an error. Error is actually an interface. How the type looks in detail, we won't talk about this here due to time constraints. But it's actually just also again a struct of two pointers, which you can create yourself, or if you have a Go binary which has not been obfuscated. As I said before, IDA recreates the types based on the program counter line table, and so you can simply use these types to retype the variables. And if you have a sample which has a corrupted program counter line table, you can, what I usually do is I open a second binary which has not been corrupted, and I just import the types from there over to my database, which has which is missing the types. Because the runtime types, if you manage to get the same version, they are the same. So you can just transfer them from a correct binary to a binary where the table has been corrupted. So if we apply this type, suddenly the code looks like this. So it gets way larger, and IDA now also understands where the branches are. So this is like a typical case which you often have when analyzing Go binaries, where the decompiler simply lies to you. So you really cannot rely on it only. You really have to look at the disassembly and help your tool of choice to understand what's really going on. But if you do this, then you can actually get quite a nice output, which is humanly readable, is maybe different, but it's closer to it. One thing when dealing with obfuscated binaries is that IDA, by default, tries to parse the Go version from the module info structure. And depending on the version used by the binary, it sets the calling convention. So if you have a version below 1.17, it sets it to the stack-based calling convention. If you have a binary which is above 1.17, you get a register-based calling convention. If you have a binary which has this meta information corrupted, IDA will default to the stack-based calling convention. But as I said, since at least 6 minor versions, this calling convention is not used anymore. So your functions will look like this on the right. It will still recover by using function signatures many of the function names, but all the functions seem to get no arguments. There's a simple fix for that. It's like a small tip for the IDA users here, is you can actually force the calling convention with the -o golang force rec.lv command. And if you do this, the same function suddenly looks like this. So these are just like these very small things that you sometimes need to help IDA with understanding, and then you will get a much more refined output. So let's get to one of the core features of Go, which is Go routines. I've already mentioned this effortlessly concurrency paradigm that they are following. So they introduced this Go keyword, which you can see on the left, which allows you to launch a function asynchronously. So you can call functions like just normally, and you can prepend the Go keyword, which will then launch them asynchronously, and you will get, for this example, some output like this, because these two functions seem to be running in parallel. This is very easy to do, and the Go language by design encourages you to use these concurrent operations. So also in Go malware, you will very often see heavy use of Go routines. So we need to understand how this looks like when we see it in disassembly. So what you actually see here is, as often with Go, as it was also with strings, you will just have some more layers of indirection to the function calls. So when a Go function is, so a Go routine is called, you will see something like this on the right. So you will see a call to runtime new proc, which will get an offset passed to it. And behind this offset, you will have a wrapper function. If the function gets some more arguments, they will also be passed to this runtime new proc function, and will be part of one data structure. And this wrapper function then, this again then calls the actual function. So it will do some preparationary work, and then it will actually call the function that is being called. So it's not that hard to understand, but it's a bit annoying in a practical sense, because when you have this high-level look on a Go function or on a Go binary, then you do not directly see the calls to the functions that are being made there, because they are hidden between behind this one more layer of indirection. A feature which is very related to Go routines are channels. Channels are the mechanism of Go to communicate between different Go routines. So they are basically, channels. So they are a data structure where you can put stuff in and get stuff out. They are not like a queue in a sense that you can put multiple, like a buffer queue, where you can put multiple parts of data in and then get everything first in, first out style out. But they are actually a blocking operation on both sides. And they can be used like this on the left. So they are created with the make keyword, which is also created to create different data structures. And then they can be passed to a Go routine as an argument. And then one routine can read from it, like you can see on the top, and the other routine can write to it. This is like a very easy kind of inter-process communication mechanism to communicate between Go routines, between different Go routines. So how does this look like in the decompiler? It's actually quite simple, because it basically directly translates. So at the beginning, we have a call to a runtime function, which is called runtime make chan. And it will get, as an argument, a structure which defines the type of the channel which should be created. If you have a binary which is not obfuscated, you will have it directly annotated. Then the Go routine is called. And this is this thing that I've told you about on the slide before. So here a new object is being created. So this, before we saw the disassembly view, this now is the decompiler view. A new object is being created, and there's first this main GoWrap function which is being written to it, and then on the low end you will have this v2 which is written to a different offset of this object. So this and this object is then passed to the runtime uproc function, which actually launches the Go routine. So it passes the reference to the wrapper function, which will then actually call the Go routine and the argument to it. And here's also something that you will very regularly see when you look at Go binaries in the decompiler. You have these very many variable reassignments. So this v2 variable, it is assigned to the channel actually, but in two different places, because this big branch which is happening here, it's like some runtime garbage collection stuff which is happening, and depending on some internal runtime workings, it would just operate in a different way. But the gist that I want to tell you with is that you very often have the case that you have like objects being created at the top, then they are passed around variables created by your decompiler, like a whole lot, and then finally they land somewhere. And it can be quite confusing to follow this data flow. So here the best thing that you can do is that you look at the function calls that interest you and then just go back and traverse all these assignments until you reach the point where they are actually being created or assigned. So here this, as I said, the Go routine is being called. And then a message from the channel is trying to be received. And this is done with also with a simple runtime function, the runtime channel receive function. It just gets two arguments. On the one hand, it gets a reference to the channel, and then a memory address where the resulting value should be placed. And then at the end, channels need to be closed, so you also have a call to this runtime close channel function. And if we look at the channel function, it's actually quite simple. It gets as an argument the channel, so you can also clean it up a little bit, and yeah, you just use the equivalent of the runtime channel receive function, the runtime channel send function to write stuff to the channel. So yeah, a thing that I wanted to mention, because it looks very similar to Go routines in the decompiler, is the defer statement. Defer is a statement also introduced by Go, which basically tells the program, hey, perform this function call at the end of my function. So you literally defer it to the end of the block. So this program, which we have here, which just calls print line with a defer keyword 10 times, it internally creates a stack where all of these function calls are placed, and then at the end they are handled like in reverse because it's a stack. So the output of this would be like the reverse counting from 0 to 9. Of course, this program doesn't make much sense, but what defer is usually used for is for doing cleanup work at the end of the function, so you don't have to remember to do this at the end of every error case. For example, if you have to close a channel at the end of a function, you can create it, and then you can defer the closing of the channel, and you don't have to think about it again. And how this looks like in the decompiler is actually very similar to how Go routines are handled by the runtime. So you have an object which is being created with a wrapper function again. Now here it is called defer wrap. Before it was called go wrap. And then you have a function called runtime defer proc. And this will basically put this function call on the defer stack. So it's basically, the structure is the same as it was for Go routines. And then at the end of a function, there will be a call to runtime defer return. And this function will then handle this stack of function calls which has been placed during the function, and will call all the functions in reverse order to perform these cleanup operations. This defer thing can also be inlined by the compiler. So if you only defer one function and there are not many conditionals, then usually the compiler will inline these calls. But from a perspective of reverse engineering, this doesn't matter that much for us, because then we actually just see the function calls and don't have to have this layer of indirection, and we don't have to go through these defer wrap functions. Okay, then there's one thing that I also want to show you. Here we have a, it's a peculiarity of Go programs. Here we have a simple program which just creates two arrays. One is initialized with some values, one is initialized by as 0 by default, and then we just have a function which prints this. And if we look at this in IDA, it looks like this. So first of all, there are many casts. This is also a regular thing when dealing with Go binaries. So I usually, first thing I do is just turn off all the casts, so you don't have to have an ultra-wide screen to see everything. But then, as you can see here, we have calls to memory locations. So these are not locations which are identified as functions by IDA, but they are just locations in the program. And if we look at this, we see something like this. So a very, very long function, which is just like a linear set of instructions. And if we look at the disassembly, we can actually see that it's a repeating pattern. So we have some pointer in RDI, and then you always have this repeating pattern of 5 instructions. So the value at the pointer and at the next offsets is set to the contents of this XMM15 register, and then the pointer at RDI is increased. And then the whole stuff repeats until the function finally returns. And this is actually an optimization used by Go to zero out buffers of different sizes. So XMM15 is actually a special purpose register in Go, and you will see it regularly all across the place. And it is just always a 0. So this is the register Go uses when it needs a 0, and it can be used to zero out other memory locations. And the purpose of this very long function, and the reason why we see calls to these memory locations, is that this is first of all, it's an unrolled loop. So you could also do this in a loop, but the advantage of doing it like this is that you can use it to zero out buffers of different sizes, because you can simply jump to, or you can call into the function at different offsets, and then depending on where you start, it will zero out a buffer of a different size. This is actually like a quite nice little optimization, but it results in this, that you have these calls to some weird-looking locations. But if you see this in Go binary, it's usually one of two things. It's either this, so it's a zeroing mechanism, or the equivalent. Yes, this is the registers. The equivalent is the DAF copy function. So the previous one was called DAF0, named after a programmer who worked at Lucasfilms, who was tasked with optimizing these kinds of operations. And here is like an equivalent function which is called DAF copy. And as the name says, it basically does the same thing, but not for zeroing out memory, but for copying buffers. So it is also this unrolled loop structure which will help you, or help the compiler to efficiently copy one buffer to another thing. This is, you will regularly see this when arrays or large data structures are either initialized or passed by value to functions. Yes, so we're nearing the end of my talk. Just some useful tools that you can use in practice. The most useful tool of everything, as usual, is the official Go reference. So the easiest thing that you can do if you have something in your binary that you don't understand is try to recreate it. Write a small program which does this one thing that you don't understand, like you have a crypto function which is being used and you don't know where the key comes from. Write a small program which implements the same crypto function, compile it, preferably on Linux with debugging symbols, and look at it in IDA. Because if you provide IDA with debugging symbols, you will actually get quite a nice output, and it will help you correlate what's actually happening in the program. Another small tool that I like to use just for a quick first look is redress. It's a small tool written in Go which parses this PCL-NTAP structure and can give you some information about it. It also has some integration for a radar array if you're like a user of that. And it can give you like this small overview about how many functions are in the binary, which compiler configuration was used, and a thing that I like to have a short look at sometimes is it can give you a source code projection. So it will show you all the source code files and how many lines they had, and you can get like a quick insight in how this binary that you looked at was structured when it was programmed. It is built on a library called Gore for Go reverse engineering. It's like a nice, small Go library if you want to write your own tools, which provides you with some nice functionalities in regarding to parsing this PCL-NTAP structure. Another thing which is like doing the same but more is Gorism. It was created by Google, and yeah, it basically does the same thing as redress, but way more. It also comes with plugins for multiple different disassemblers. I think at least for IDA, Ghidra, and Binary Ninja, and yeah, it's basically tries to fill these gaps that some of these tools have when it comes regarding to parsing Go binaries. Another thing that I've found quite useful in the past is CERT.LV. CERT.LV is like a semi-official Go debugger, which is not directly targeted at reverse engineers, but more for developers. But it also parses all these Go structures. So what you can do is you can use, for example, the funcs command, and you will directly in your debugger have all these functions in from your malware that you're looking at, and you can set breakpoints on it. In practice, it feels a bit like GDB, but worse, because it handles a bit like GDB, but it's missing many features. But especially on Linux, when you just want to do some quick binary analysis, get some values out of some registers, I think it's a nice thing to do because you don't have to like calculate around with memory addresses if you have a binary where the PCN tab is intact, and can get just some quick results. And one other thing, also some kind of advertisement, a colleague of ours, Daniel Ploman, which many of you probably know as the Malpedia guy, created this tool called mcrit. It's a binary analysis framework which you can use to compare binaries on a basic block and function level. And one thing which it was not created for, but what you can do is when you have binaries which have malformed PCLN tab structures, is you can load as many Go binaries as you can build from different versions into it, and then use, for example, the IDA plugin to correlate the internal runtime functions to the functions that you have in your created benign binaries. So you can use it actually to rebuild the symbols in your binary of the runtime functions, even if the PCN tab structure, for example, has been corrupted. So that's it from me. Thank you for listening. Thank you for having me, and have a great rest of the day.
All right, thank you. Before that, with the applause to the presenter, I would like to open up the questions. Also, we can take one or two questions from the audience. Is there anyone who wants to ask a question from the audience? Okay, I will kick off. At least I will ask one question from myself, and there is also one question that's been sent in remotely. Now, you mentioned that the Go compiler has been moving now to kind of put all the variables into the registers. To my best knowledge, I know that the GCC also uses on 64 bits, also the registers to store all the variables. That minimizes the stack usage. Now, coming down to this, you said minimal use of the stack. However, still the backtraces will be available through the stack so that we can see the call chain, or that is stored somewhere else. How would the stack minimal use would be implemented? Does it rely on other structures, like heap, outsourcing somewhere else?
So I'm actually not sure if I can answer the question. I mean, the arguments are passed around in the registers, but I'm quite sure. I cannot say it at 100% certainty, but I'm quite sure that return values are still placed on the stack, so it allows recreating these stack frames, as well as local variables are also placed on the stack. So there are still some function frames on the stack which are present. It's just the arguments which are, if possible, passed on the registers.
All right, I will take the question from the menti.com. The question is about the obfuscation of the Go binaries, and there's a specific tool that the question author asks, Garble. I'm not sure if you're familiar with it. Yeah, you are. And the question is, like obfuscation of Go binaries, will it be flagged by the antivirus?
Yes.
Yeah.
So when I created the workshop, I created some reverse engineering tasks for the participants, and I created a very small benign binary which was just like the simplest of crack me's that you can think of, and I just obfuscated it with Garble, and Windows Defender kept removing it from my system. So even though I wasn't dealing even with malware, I had to disable the Defender on my system or on the system for the workshop participants, just to enable them to have a look at these obfuscated binaries, because as of now, Windows Defender seems to be very strict about this. So they just don't even care if you have actual malware or not. They will just kick it off your system.
before you depart, do you see the tendency to increase in the Go malware? Is it more dominant? Is the Go the dominant malware language, or you still see that other languages are still there?
Well, I think C is still the main language, and it will also remain that way. But in my personal experience, it's increasing because it's easy to write and it's cross-platform, and you get this many nice features. Garble is also, like, from a malware writer's point of view, a very nice obfuscator because it's super easy to use. You just, instead of Go build, you write Garble build, and you have an obfuscated binary. It can introduce these nice things like control flow flattening, and it will obfuscate all your strings, corrupt all these control structures. So it's like a very low effort, high reward thing. But I don't think it will overtake C, but I see it increasing. Yeah.
All right, you have absolutely deserved the candy and the socks. So thank you for the talk. Let's give a round of applause.
Thanks. Thank you.
With this, we will give next presenter about 2 minutes or so just to set up and connect, and we'll see you soon. All right, we are ready to continue. The setup was very fast and efficient. As I said yesterday, we've sacrificed the keyboards and memory chips in the server room. So that is where the gods of the tech are with us. Now with this, I would like to introduce our next speaker, Patrick. He will talk about the reverse engineering and the insights of a particular botnet malware. So with this, Patrick, welcome on the stage.
All right. Hello, everyone, also from my side. My name is Patrick, and I'm the team lead of the threat analysis team at VMware. To be honest, I won't really introduce myself because this is usually a very boring story. Instead, I would like to start a bit differently today, and I would like you to just imagine you're being a person that is responsible, or part of a team that is responsible for the cybersecurity in an organization. And you just go to work on a Thursday morning. Everything seems to be regular, everything seems to be fine, nothing is happening, you don't see any kind of alerts. At the same time, a threat actor is actually also going to be active and coming up with a new malware family that is just getting around the world in the end. But you still don't see any alerts, right? And somehow, unfortunately, they're managing to walk just past you, to walk past your security solutions, your security measurements, and you still don't see any alerts. And at a specific time, maybe a couple of hours later, or maybe even a couple of days later, you realize that something in your network starts to behave strange or differently. Maybe users are going to report that something is wrong, they can't use their machines anymore, because in the worst case, there is just a pop-up message on any desktop saying that this machine has been infected with ransomware. And this, of course, is probably one of the worst nightmares that to security folks, as we all are, can happen. And unfortunately, this seems to be case, or this seems to have happened with a malware family which is called Pikabot in the past. And I think we are here to just share our stories, share our expertise, and also share our knowledge to just empower the community to be strong for the future and avoid such situations, of course. So in today's talk, I would like to focus about Pikabot, about its evasion techniques, in particular about indirect syscalls, But before we dive into this specific topic, let's provide a quick overview on what Pikabot actually is. So it's a malware family that has been appeared in early 2023, so it's relatively new. It's 1.5 years old. It's classified as a loader or a downloader, which means it's supposed to infiltrate networks, get persistence there, and in future stages just download additional payloads and execute them. The threat actor that this is related to is known as TA577, which I guess probably all of you have already heard about them. They are responsible and well known for distributing QBot or Quackbot in previous years, and they were very, unfortunately, successful with it. QBot has been shut down, so essentially they needed to search for replacement, and this is then when Pikabot came into place. They are also known for distributing blockbuster ransomware and making quite a good amount of money with it, which also highlights how important this actually is and how serious this threat is going to be. Yeah, and Pikabot is known for its evasion techniques. It doesn't only contain evasion techniques, it also contains obfuscation, just everything that makes our lives as reverse engineer, as analysts, as security analysts, anywhere, way more difficult. And one part of this actually is indirect system calls. Taking a bit of a closer look to understand what we're going to talk about, Pikabot consists of 2 different modules. On one side we have a loader, and on one side we have the core module. The loader is basically responsible for just loading the core module, and as the core module is essentially the heart of this malware family, it also is protected in some special ways, and the loader is responsible for unpacking the stuff and then basically executing the core module. The core module, as its name, is responsible for everything else. It's doing command and control server communication. It's responsible for injecting additional payloads, doing command execution, but also doing some data collection, or actually fingerprinting of the infected system. So you may wonder why we actually even talk about Pikabot, because in 2024 it went dark, so it was basically shut down due to Operation Endgame, which was a huge law enforcement tasks that just killed a couple of different botnets, and Pikabot was one of them. Even though the malware family itself is dead, this doesn't really mean that the techniques and all of the nasty stuff that they've implemented there is dead, right? So the techniques that they have used, they are still alive, and they will be used by other threat actors and in other malware families as well. So I think this is actually quite a good example why we still need to talk about this. And we also probably expect there are some additional threat actors coming up, picking the same techniques, maybe advancing them even more, extending them. So we should still be aware of what has happened there and what might be happening in the future. And this brings me actually to the evasion techniques. So we will start now covering a couple of them that we have seen. We still wait a bit with indirect syscalls before we actually dive into the fun part. So a couple of them that we have highlighted, and I think those are relevant and interesting anyways for also other malware families. And one is the hardware-based evasion technique. So this is actually not new at all. We know those are there for some years. And also usually just checking for resources to determine whether the malware is running on a virtualized, maybe analysis environment, or if it's running on a real machine. Usually those checks are actually quite funny from my point of view, because they are checking for if the system has more than 2 CPU cores and if the system has at least 2 GB of memory. To be honest, this isn't really telling anything, because I don't know if it's even possible nowadays to buy a machine that has these hardware specifications, right? Even smartwatches have more than this. So those checks are there for years and they have never been really touched. But we do see actually a trend since this year that those checks are getting adjusted as well with the time being. So instead of checking for 2 CPU cores, they start checking for 4 cores, and instead of 2 GB memories, they also start for checking for 8 GB memory, which is still probably not really a very, very difficult check to detect, and also very difficult to get around it, but just we need to keep in mind that threat actors slowly starting to also adopt basically with the time. Another check we have is the language-based evasion. So essentially, this is also nothing new at all, but it's still important to highlight this, and we see 2 different use cases for these language-based evasion checks. Well, it's maybe not even a full evasion check, but it also has some different purposes in the end. So on one side, this can be used to target specific countries, specific languages, basically. In the keynote, I think yesterday from Robert, from ESSET, we have seen that this banking Trojan he was talking about was mainly targeting Latin America-based countries. Right? And this can, of course, be done via languages, for example. There are lots of different artifacts on a machine that you can use. So you can target a specific group with them. And the second option that this can be used for is, of course, to avoid infections in specific countries. And this is also what we see usually in some of those malware families, especially if they have been developed in former Soviet Union countries like Russia or anything like this. Then they usually avoid infecting devices in their own countries, because this also prevents them a bit from law enforcement on at least their own country. So this is the second option why this is often being used. Then we have timing-based evasion. Well, that's also nothing new, right? We all know that doing some sleeps, waiting on some specific events or actions has been used for years. The main goal for this is just to pause the sample execution as long as possible to maybe avoid a successful detection either in a sandbox or in an emulator. However, for Picabot, we have seen something that is kind of new, and this is the use of a quite uncommon API, which is called beep. So beep is a Windows API that's essentially supposed to make a beeping noise on your computer, and it's blocking in the end, right? As long as this noise should appear, basically, it's just doing nothing. Unfortunately, we weren't really able to get this beeping noise out of any machine, so it looks like the API is also quite old and doesn't really work on modern systems anymore, but the API call itself still works, right? So it just takes two arguments. You have a frequency and you have a duration, and if you set a duration of like 10 minutes, for example, this API call will just pause the execution of the sample for 10 minutes, maybe used to get past some security tools. And this is kind of new because we haven't seen beep being used before, and if you're not mistaken, Picabot in its early days was also called as beep loader, or was also referred as beep loader, which is basically based on this API call. And another check, which of course is also something that we see commonly, is checking for sandbox or emulators. In this case, they made use of trying to load fake files. To be honest, this doesn't really affect sandboxes. There might be some exceptions out there, but emulators, I think, are usually more affected by this one here. So essentially what they're trying to do is saying, well, please give me, or I want to open file which is called foobar, whatever. And a regular system would say, oh yeah, sorry, this file doesn't exist, so I can't open it, it's just an error, right? On an emulator says, well, oh yeah, you probably need this file to run successfully, so here it is, please take it, even though it doesn't exist at all, right? So this can also be quite easily used to detect some of those emulators or some sandboxes probably. And then, of course, finally, we have the interesting part, and this is the monitoring or hooking-based evasion via indirect system calls. And this is, of course, where things are getting funny, exciting, and also a bit more technical now. So before I will jump into this topic, I have two disclaimers here. First one, of course, there is a certain complexity around this topic, and within 45 minutes, it's quite difficult to explain all of it. So we probably have removed some of the complexity here to just save some time, and you might encounter that some information might be missing, but this is hopefully on purpose at least. And the second one here, about this whole story of direct and indirect syscalls, I mean, there's a lot of discussion going around in the community. There is also a certain confusion whether something is being referred as direct syscall or something is referred as indirect syscall. There's also where opinions are actually going into different directions. Based on what we are presenting here today, this is on our own experience, and this is also at least how we understood this whole topic. There might be some people disagreeing with some parts, but I'm of course happy to also take some discussions afterwards on this. Yeah, before we start, we of course need to look a bit into the Windows API to understand what is happening. So we have this little chart here that we will probably see in a couple of slides now, maybe even through the rest of the presentation, where we just see a bit this control flow, execution flow, on how to get from an API call to basically kernel code execution in the end. And this is how it should look like, or this is how it's expected to look like on Windows systems. So we have here on the left side a user mode, we have on the right side a kernel. We're actually not really interested in what the kernel is doing, we're only interested in what this path is from user mode to kernel mode. And over there we have a sample that is being executed somewhere in the process, and it just has some instructions in it. And at a certain point it wants to create a file. This is just a demonstration API call, could be anything else, but we say we want to create a file. So usually what is going to happen here, you make use of the Windows user mode-based APIs, which has an API function called createFileW, which then refers to, and this is where the first complexity has been removed, usually to kernel 32 DLL and then to kernel-based DLL, but as this is usually just a redirection due to backwards compatibility, we just have removed this step. So we're somewhere being in kernel-based DLL, where this API is implemented. It has some instruction, maybe doing some checks, doing some validation. And then it continues and calling the native function for it, which is then in NTDLL, which is called NTCreateFile. So this is usually the lowest level before the kernel mode execution is going to happen. So we have some instructions here as well, and at the end we do have this syscall instruction, which just indicates to the CPU, well, now we want to switch from user mode to kernel mode because we are performing an operation that requires higher privileges. Creating a file, you need to touch the hard disk, you need to maybe access some drivers, resources are managed by the operating system itself, by the kernel, so basically that's why we need it. Once this is done, once kernel has finished execution, all the way is actually just going to be back up where we came from. So this is how it should look like. As modern systems, or usually all systems in organizations, are having some sort of antivirus installed, maybe also even having some EDR systems running, they are starting to monitor stuff that is happening, right? And of course, there are different complexities on the systems. They have different ways of being implemented. They also sit on different locations. At least for our talk here, and this is just a very, very simple demonstration, we said we have an EDR indent hook on any of those user mode APIs. So as an example here, we still starting with the same example. We have createFileW. It's going to kernel base, and for example, in kernel base, you can see a jump instruction instead of the code that we've seen before, which then just redirects to the EDR itself. The EDR then has the capability to look into this API call. It can monitor it. It can walk through these arguments that have been provided. It can scan them. It can scan buffers, whatever it wants to do, and can then decide whether it wants to continue the execution or blocks it because this seems to be dangerous. In this case, we are continue, which then just continues the execution. We are going back to NTDLL. We're having the syscall, and we're going to the kernel in the end. Just for sake of completeness here, this EDR hook would likely be somewhere probably in NTDLL because it's the native function. It's lower to the syscalls in the end, and there are also less functions available in this. But keep in mind that this is just a very basic example. So, of course, threat actors want to get around this problem because this is usually very annoying for them to get detected. So what can they do? And there, of course, are very much different ways. And one way is instead of just using basically the existing kernel base that has been loaded during process startup, where the EDR actually also implied is hook, is just to load a fresh copy of it. Those EDR hooks are usually indent hooks that only affect DLLs that have been loaded into memory already. So instead of using this one, you can just replace it with a fresh copy of the file, and then you basically would be gone. A different story, it could also just pass it and try to find those hooks and then just patch them out. It's also just a very simple way. Same, of course, applies if the hook would be in NTDLL. You can just replace it in the end or load a fresh copy. And then we would go there, we have the syscall, and the EDR, at least if it's a user mode EDR that relies on hooking only, would be blind in this case. A good story about this, we are usually already in a time where hooking-based EDRs are, I think, quite rare, and they usually at least rely on multiple different indicators and not only on user mode hookings. Well, so now it's a question. We have those APIs from kernel 32, from kernel base, and then we go into the native stuff, and then we have the syscall. So what's even the point of using all of those APIs in between? Why can't we just use native functions directly? So for threat actors, of course, they do it already, and this is something that we see quite often. Even though Microsoft or Windows specifically doesn't really want you to use them because native APIs are, at least first of all, less good documented. And on the second side, they are subject to change. So it's not really guaranteed by Microsoft that the native API remains to be completely the same. For user APIs, though, it should be the case. But how would this look like if we are going to use native APIs? Well, instead of calling createFileW, for example, we can directly call NTCreateFile, and we can jump over this part in the middle, and we go into the NTDLL directly. This is possible because of lots of researchers have done an incredible work here and also still doing this and reverse engineering all of the Windows internals, because you still need to know how this API needs to be called, right? So it's native API, it's already not really ready for official use, basically. So arguments are not really good documented. Some of them are, but at least to researchers that have reverse engineered all of this stuff, those information is already available. So based on this, it would be quite easy. You can just call this directly. You go into entity.dll and you have basically the syscall to go into the kernel. And this is something that is being used very, very often in malware as well. Yeah. It has the power to maybe bypass some of the inline hooks that are being on higher level APIs, but of course, it still would be catched if the hook is somewhere placed in entity.dll. Just to see or to display and show how simple this is, you basically just need, in theory, 3 lines of code. Of course, this is a bit simplified, but you just need to get a handle of the DLL. You need to get the address of the function you want to call, and then you need to prepare all of the arguments, do some prototyping, and then you basically can use it directly. So it's a couple of lines of code, and you essentially can directly use native APIs. Well, that's the question, and this is now basically a bit of the story, what has happened with all of this topic here from going to direct system calls to indirect system calls. So what would be the next approach, what we have seen in the past that has been used to basically get a bit more in depth here and avoid inline hooking in native DLLs? So isn't there a way to maybe go from the sample itself that's being executed directly to the kernel, so leave out all of the layers in between that are coming from the Windows APIs? And yes, of course, there is. Otherwise, I probably wouldn't have asked the question, right? There are direct syscalls. Direct syscalls are around for a couple of years, and they are being used actively. To know or to understand how those direct system calls are working, we have to look very briefly into native functions first, because native function is usually the last step before kernel code execution, so we just need to understand how those are being implemented and how those work. So for this, we do have a short excerpt here of ntdll, which is for ntcreate file, which is something that we refer as a syscall stub or system call stub. And this is basically the only code that is in ntdll for ntcreate file for this function, and it's just 6 lines of assembly code. We have a move instruction at the beginning, which just shifts around some arguments, some registers basically to preserve some arguments. And then we have another move instruction that moves the value of 55 into EX register. And this is a very important value because this value is the system service number or syscall ID, however you want to call it, that tells the kernel later on during the syscall which function needs to be executed. On this machine where we have looked into this, it's 55, so just keep in mind that this value is subject to change quite frequently. If I'm not mistaken, it even changes on minor version of Windows system, not only on major versions. And this is also, of course, one of the reasons why in legitimate software you definitely should not use them directly hard-coded, which you actually should not use direct system calls in the end at all. But for threat actors, usually don't really care, or they just pass those values out before. Then we have another test instruction and the jump not equal instruction. We can completely forget those two here for our presentation here, because this is usually just to check whether this is a 32-bit process or a 64-bit process, and we are only looking here at 64-bit basically. Then we have the syscall, which transfers the code execution to kernel, and then we basically have a return statement, and that's essentially everything. So this is not much, right? And this is the only thing that needs to be understood, besides arguments that are being passed to this function, of course, to make use of direct system calls. So looking into implementation here, it's also just a very quick example. All the way down below, you can see those couple of assembly instructions that we have just seen in the syscall stub before. We are moving the registers, we are preparing the number of the syscall, and then we're just calling syscall. To make this a bit easier to use, we have wrapped this into another function in C, because then the compiler nicely takes care of cleaning up the stack and so on, so we don't really have to deal with this one. But as you can see, it's also only a couple of lines of code, and you can basically make use of direct syscalls. And then, of course, depending on the complexity of your EDR, this might be able to get around this hooking in ntdll as well. So how would this look like? We basically prepare everything in our sample directly, and we have the syscall instruction, and we directly jump into the kernel, and everything else is basically out of scope. It's not really needed. This was also, I think, quite an effective technique that has been used. Of course, nowadays we are aware of this, and it's also, of course, on the other side, not that difficult to detect. So if you remember, in the beginning, I have shown this whole path basically from the sample to kernel to NTDLL, to kernel base to NTDLL, and then to the kernel itself. So all of those different DLLs have different addresses, we have different regions, and inside the kernel, it's actually usually the case that you're coming from NTDLL into the kernel, and also the kernel returns back to NTDLL. So in this case, we're actually coming from a completely different region, from different symbols, and we also go directly back over there, which also means that it's quite easy to detect this in the end. As an example here, you can make use of the Windows event tracing. You can install some callbacks there. There's a nice way you can have a callback on every syscall instruction that is being executed. It provides you some insights on basically where it comes from, where's the return address, and so on and so forth. And that's quite easy just to figure out from which location the syscall has happened and where it's actually going to return. So this is quite an easy way on how to detect this. And this, of course, then raises the question, is there something else that we can, or that threat actors basically can make use of to get around this problem? And yes, of course, there is, and then this is the point or the time where we actually come into indirect system calls. This is just another way on how this, in the end, can be used. We're having the same setup here, basically, but instead of calling the syscall instruction directly from the sample itself, we are just making use of a jump instruction and jumping somewhere into NTDLL, into the NTCreate file function, for example, where syscall instruction is being located. So we're just making use of existing CPU instructions somewhere else to make this whole execution flow look like more legitimate. And this is, of course, also something that we have seen. It's being used in the wild, and especially in the beginning, it worked quite well. Of course, there are some different ways here how you can do this. You can maybe jump to the specific offset for NTCreate file and let the system service number being set there. You can set the system service number in the sample directly. A lot of different ways. And also from an implementation side, I mean, just if you get into this topic, it might be very difficult at the beginning, but if you understood this actually correctly, it's very easy. The only thing that, of course, we need to know here is where is those syscall instructions being located, and we have plenty of them in NTDLL. So it's very easy just to either rely on a fixed offset, which is possible, but not 100% of the syscall stubs that we have in NTDLL are look completely the same. The majority of them does, but some of them are a bit different, right? So you could either rely on a fixed offset, like this one here, it's in hexadecimal 12, or someone could just also simply parse the export table, get into each of those exports, and then just trying to find the syscall instructions. It's quite easy. From an implementation point of view, it's also quite simple. The only thing is we have the same code below there, we have the same instructions, but instead of calling syscall directly, we're just having this jump instruction, and we're jumping into an address which is basically, for example, for NTCreate file at the offset of hexadecimal 12. And based on this, yeah, you can just simply make use of indirect system calls here. Well, this now brings us actually back to Bicabot again, and to something that, not fully sure if this is actually a valid official name, but we called it indirect random system calls. This is something that we have seen in Bicabot. What is this about? So we have the same setup as we have before with the indirect system calls. We have again our sample, we're preparing the syscall ID, and then we're basically jumping to NTDLL where we have the syscall instruction. The only difference here this time is instead of jumping directly to NTCreate file, we are jumping to a completely different function which is called NTCreate atom A, or anything else that you would like to have. So we're having a completely different function that we basically use, but we don't really care about all of those functions. The only thing we care about is the syscall instruction, because that's the most important thing we need. Everything else that is happening before, swapping around some registers, preparing the syscall service ID, this can still be done in the sample, because these are just some simple CPU instructions, and they do not rely at all on anything that is basically here. So this adds a completely new layer of confusion in the end, right? So just imagine if you somehow have a monitoring tool that's somehow maybe sitting between NTDLL and kernel, or maybe in kernel. So you're basically come from a region that is for anti-create atom A. You would expect specific arguments that are being used for this function, right? However, and of course you would also expect a specific syscall ID, right? So then you go into the kernel. If you then inspect this stuff in more detail, we actually having a different syscall ID, so it doesn't really match with what we can see here. And we are going to call anti-create file, right? Anti-create file has completely different arguments to the function than anti-create atom would have. So this is not a point where this confusion starts to happen, because if an EDR or something else would start to analyze those calls that are happening, it tries to interpret the function arguments that have been passed to this function, right? And they don't really match anymore the expectation, and this actually seems to have caused quite some troubles with various different solutions when Pikabot actually started to make use of this. Yeah, and then basically we go to the kernel executes the stuff, and the kernel actually only is interested in the syscall service ID. It doesn't really care which function it was, because based on the ID, he knows what to execute. And the arguments are still there because this have been prepared in the sample before. From an implementation point of view, this is actually as easy as the one that we had before with indirect system calls. We have the exact same assembly code below, but just instead of using the offset for anti-create file, we just use a different function. It doesn't really matter. It could be anti-create atom. It could be anything else that you can find in NTDLL. You just need, of course, to have the offset, because we only want to execute this syscall instruction. Well, and this is, as mentioned before, what we have seen in Pikabot. And to be honest, when we have seen this, we were quite surprised and impressed, because I think this is a very smart idea. Yeah? And for some reason, I was not fully convinced that the threat actors actually came up with this idea by themselves. I think this requires some research. This requires a lot of time that they need to play around with this stuff. So there was a certainty of, I wasn't convinced that this is indeed coming from them. And due to a funny coincidence, we actually came across SysWhispers 2, which is just a well-known framework that is available on GitHub, basically. And after we looked into those things together, we just realized that this is completely the exact same implementation. So essentially, threat actors are also quite lazy, I think, and they probably just observed what is happening in the security community, figured out that SysWhispers 2 seems to be interesting, funny, and they just have taken this project, embedded it into Pikabot, and yeah, voila, you have basically quite a good evasive sample in the end. And it's somehow a bit scary to me as well that we have only figured this out in Pikabot. We've tried to search a bit through the web if there is any reference that malware actually makes use of SysWhispers, but we haven't found any information on this part. And due to another coincidence, actually, we came across an old Qbot sample, which I think was from May 2023 or even from 2022. I'm not fully sure on the date anymore, but it was at least more than 1 year old, which actually also had completely the same implementation there, which just highlights that indirect random syscalls, as we referred over here, have been used for quite some time already, but yeah, it looks like it was just pretty much uncovered at this time. And this is also one of the points where actually this confusion with direct and indirect syscalls starts to happen, because for us this is actually an implementation for indirect system calls. You never directly call the system call, you make use of existing instructions. The developers of SysWhispers 2, maybe we are wrong or maybe there's the confusion, the developers of SysWhispers 2 actually announcing this as direct system calls. So this is kind of the confusion that I've mentioned before. Well, now let's going back to the present and maybe even into the future. So this is what we have seen in Pikabot in the past, right? And of course, I've mentioned that before. Other threat actors they have already adopted those techniques. We have seen this in other families as well. So it's just out there, it's being used, even though Pikabot itself is dead. And this caused us to actually start thinking a bit more in the future. So if we have seen this, and this is basically coming from some open source project, what might be there that is already out there maybe as research projects that could be a potential target to be used by malware as well in the future? So we did a bit of research and looked into this topic a bit more. And one of those interesting things would be the combination of vectored exception handling and syscalls. So all of this, what I will show right now, is nothing that we have seen yet in malware and malware families, but this has been already researched, and it's likely to be a case that maybe the same thing with Sys whispers can happen in the future, and we will also see this. So what is vectored exception handling? Just a quick recap on this. It's a tool that you have on Windows that you can basically allows you to register functions that can handle exceptions that occur in your program. And this is actually very powerful, because if the exception occurs and your callback function supposed to handle the exception is being called, it allows you also to modify all of the registers, and of course this also allows you to completely change the control flow, right, as part of the exception handling, which is kind of ridiculous, because completely changing registers and the control flow might not be the initial intention of handling exceptions. Yeah, and this can also be used in this case, and we have experimented with this as well. So as an example, seeing our sample again here, we execute it, and at a specific time, basically we register our exception handler, and at a specific time we want to create an exception. There are various different ways how you can do this. It's either jumping to an invalid address, trying to read from an invalid address, having a division by 0, doesn't really matter. As soon as the exception occurs, we're basically going into our exception handler function that, yeah, the developer controls. And as we have seen before, for all of those syscall stubs, we can essentially just do the completely same thing again. So we're swapping the registers basically, or we're moving the values in the registers. We are preparing the syscall number, which was hexadecimal 55 in our case, for the ntcreate file function. And then we are setting the instruction pointer to any syscall instruction that we can find in entity.dll again. In this case, we just used ntcreate atom again, because, yeah, it's a good example, and it's one of the first ones in the end. So an exception occurs, then the exception handler jumps in, and out of nowhere, the execution of the sample seems to be completely different in the end, right? So this is definitely not something that might be the intended use case of this, but you can see the power of vector exception handling. Also from an implementation side, this is quite easy. You essentially just register your exception handler. You basically have your exception handler function over there, which essentially just does what I've told before. It's basically re-implementing this system service, this syscall stub. It's moving the registers. It's setting the syscall service number, and then it's just changing the instruction pointer, the address pointing to syscall instruction. So that's actually quite easy. And yeah, it just works. And it probably adds another layer of confusion to tools that have to be monitor and understand and follow this execution flow, because this is, of course, then completely out of scope what would have been expected there. There is actually also already something out, which I think is called the mutation gate. You can also find this on GitHub, which is a similar approach, essentially. The only difference is here that they are not causing any exception due to some invalid addresses or whatever. Instead, they're just setting a breakpoint, a hardware breakpoint, in one of the syscall stubs in ntdll, right? So considering our ntcreate atom thing again here, the function, so you basically just register a hardware breakpoint on the syscall instruction over here. You call ntcreate atom A as an official function, and then use the exception handler to adjust the already set system service number, and maybe also to adjust all of the arguments that you want to have. So basically completely play around with whatever you want, and when this is done, you just continue the execution. So this is, of course, the power of vector exception handling. Yeah, and another approach that we do have, of course, we all know it, is return-oriented programming, or ROP chains. It's being used usually in exploitation. If you have data execution prevention on the stack, of course, you can't execute a shellcode, so you want to play around with ROP. And you can also, of course, combine this with syscalls. Why not? Yeah, this is just a brief example how this could look like. So basically, you could build your gadgets out of ntdll. You can collect them, essentially re-implementing the syscall stub that we've seen before that prepares all of the arguments, the registers, basically. You can chain them all together and then just execute them. And the difference here is actually that this might already look a bit different if you follow the call stack, or at least the addresses, because then you actually have, again, some quite of legitimate addresses, at least from ntdll, again, somewhere on the stack. Yeah, the only thing that you need is a couple of different registers, a couple of different gadgets. You can find them in ntdll to prepare the registers, to set the syscall ID, and of course, we have plenty of those syscall and red gadgets available in NTDLL because they are usually around everywhere. You can prepare the stack layout, you can use this, and you can execute this stuff. The good thing and the good news is that just using any of those techniques that we have highlighted here today, or at least just using by one of them, this usually is, at least nowadays for modern security solutions, not able anymore to get around them completely without being notified or noticed. Because there's another technique which is, of course, inspecting a core stack. I've previously mentioned it before. So basically, if you see a legitimate Windows API call that starts with create file W, for example, you see the samples address. If you look into the core stack, then of course you have kernel 32 or kernel base, you have another kernel base, and then you go into NTDLL. So just by looking into the core stack and, for example, EDRs actually also passing the core stack nowadays, you can at least try to guess whether the chain on where we came to this API call is legitimate or not. In the case of indirect syscalls, we can see that we completely overjumped kernel 32 and kernel base, so we only get into NTDLL directly, which is quite obvious and easy to spot. And if we would use direct syscalls, of course, it's way more easier because then we would not even have the NTDLL stuff here. Of course, someone has already realized this and also looked into this stuff. So there's also, of course, the approach and idea of faking a core stack or core stack spoofing, where I can also use, again, a couple of different techniques to get around this problem. You can make use of vector exception handling, you can use hardware breakpoints again, you can rob gadgets. The main idea behind this in the end is just trying to rebuild a core stack, even though you never went through all of these DLLs and these API functions, to let it look as legitimate as possible. So this is also already something I think that is quite good working, but as mentioned again, just using one of those single techniques is nowadays not enough anymore. Maybe for specific products it is, but for the actual well-known ones, it shouldn't be enough anymore. And it should be detected, basically. Well, and this now brings me to the takeaways. So I definitely won't cover this in a summary anymore because I think it's a lot of different topics that we had here, and it's also quite technical. But what is the most important things that we can actually take here with us today? First of all, I think it's definitely not a secret, and it's definitely interesting to see that the goal of threat actors is still to try to get around sandboxes, try to get around EDRs, try to get around AVs, so they are still always trying to evade all of these products. I mean, it's kind of obvious they're trying to stay undetected as long as they can. They're trying to slip through to cause as much damage as they can do. So this is still one of their main goals. We have seen the history of the use of direct, indirect syscalls, but at least it shows us that the syscall-based evasion techniques are completely on the rise. It's not only on the threat actor side, but of course also on security researchers, on purple teams. This is an interesting technique that is being researched quite heavily, with the goal, of course, for us to find the gaps that we can fill in the future before threat actors actually coming across this and can make use of this. And yeah, of course, we live in the cat and the mouse game as usual since a very, very long time. So they are still trying to improve their implementations. They're trying to improve malware just to make our lives a bit more difficult. On the other side, it's also challenging and interesting probably. But we definitely see this sort of trend that is definitely going to continue. And one thing that is, I think, very important to mention is that if we want to be prepared for maybe what is coming in the future, like the syscalls, the vector exception handling, and so on and so forth, one of the greatest sources we can still have is, for example, Twitter, X, however you want to call it, and also GitHub, of course. Research is being published there. You can actually make use of this. You can follow it. You can try to monitor this stuff and being ready for implementations that maybe someone came up with, because there might be somewhere a gap. And then, of course, we can take advantage out of this. We can collaborate on this and improve our security solutions just to make these things that happened with Picabot, for example, not happen again in the future. With that being said, that's the end. Thank you for your time, and also thank you for listening. If there are any questions, I'm happy to answer them.
Thank you. Let's take the questions from the audience here first. Oh, there are a few, but let's take the gentleman was faster a little bit. So the race condition was one here.
Hello, Thanks for a great talk. About syscalls, does it make sense to evade them? Because if I believe modern antiviruses are hooked in the kernel, don't they?
Yeah, so modern antivirus systems and also modern EDR systems are usually already now part of the kernel, basically. There's also the more extensive Windows event tracing that can be used. So in the end, those solutions should be able to detect this stuff. But to be honest, I think this example with Picabot has also forced a lot of vendors that might not have went this step with going into the kernel, because we all know the kernel is also a critical thing in the end, force them actually go a bit deeper into the system to actually be able to detect this stuff, right? So in order to really detect this kind of things, you have to be quite deep in the system. But yes, if you be on the kernel side, it's actually quite easy to detect this stuff. And this is also the point where a single solution or a single technique we've mentioned here is not enough. Trying to combine all of them might have some good chances still to slip through to some systems, but usually not the well-known ones.
We will take the question. The gentleman was over there as well, in the red, the man in the red. You have to use the microphone.
Okay, one simple question about Microsoft Defender. Is it safe with default Windows? Or maybe you can recommend some? Thank you.
Yeah, so that's a good question. I do not feel in a position to recommend any AV solution or any EDR solution that might be good and bring you on the safe side, because that's a dangerous answer, I think. But I would say the majority of those solutions that are well known, like Defender as well, they have improved a lot in the past. And of course, they're also sitting very, very deep into the system, especially Windows Defender, I think, should be. So there is a good chance that it will at least increase your security, but saying that it's 100% security, this, I think, is a bit out of scope.
All right. I always ask a question from my side to the speakers. So before you jumped into the area of the return-oriented programming, I was listening and I was like, oh, this really resembles jump-oriented programming, where you call the gadget to jump. I mean, there's like call-oriented programming and so forth. And with the what you called with the exception handling, this sounds more like safe SEH or SEH bypass, where you intentionally trigger, right, and call to the frame. Now, this definitely depends on the libraries that are loaded and if the ASLR is enabled. Do you, in Picabot or any other malware that uses these exploit development techniques, how do they identify the library, the location, or they're not going to the fixed, right? They don't go to the fixed address. So what are the techniques to actually derive this offset? So
they usually, nearly all of them actually just rely on NTDLL, because this is a DLL that is usually loaded all the times, right? And there are various different techniques out there. You can just pass NTDLL, you basically get all of the offsets, you get all of the addresses, you can just walk through the exports, basically. So they really just use what is there, right? They don't really try to load anything specific, they just try to use whatever is there. And then, of course, I think, especially for what we've seen in Picabot, they are heavily just make use of shellcode in the end, where I can just play around and pass all of this stuff just to avoid using any additional libraries that are not loaded by default in the end. Yeah.
All right, with this, let's thank the speaker, and you have deserved socks and chocolate.
Thank you. Thank you very much. Thank you.